All right, welcome. We're going to talk about limits at infinity. So, we've talked about limits as x is approaching some point, a number. But there are lots of times when you want to ask what's happening as you let x just run off forever, bigger and bigger, say converging to infinity. Okay? And there's a similar notion for limits there. So, there's often a picture that goes along with this. Suppose your function was doing this, getting closer and closer to this line. Say this is L, this is your function f. You would want to say that the limit as x went to infinity of f of x is L. That just means as you run along this x-axis forever, your function's getting closer and closer to L. Okay? So the intuitive definition is just this. We say the limit as x goes to infinity of f of x is L if f of x gets arbitrarily close to L for all sufficiently large x's. Okay? It really just means you should think in your head as x is running off to infinity, getting bigger and bigger, f of x is trying to converge to L, getting closer and closer to L. There are, of course, similar definitions. You can take limits as x goes to minus infinity, except you just head to the left now. And you can also talk about functions as you run to infinity. It can happen that the limit is infinity, and it just means that the function gets bigger without bound. Okay? So, two basic types of examples to keep in mind. You can look at the limit as x goes to infinity of 1 over x. So how do you figure that out? Well, in this case, it's helpful to know that 1 over x looks like this. And from the picture, you can see that the answer should be 0. In other words, as you make that denominator bigger and bigger and bigger, 1 over it, of course, 1 over x gets smaller and smaller and smaller. And then the other one would be something like this. The limit as x goes to infinity of, say, x squared. Well, what does that do? Again, you need to know something about the graph. Looks like that. As you can see from the picture, it's just blowing up, getting bigger and bigger and bigger without bound. So the limit is infinity there. Okay. All right. Let's look at another example. Let's see if we can. So here, m, a, and k are constants that are bigger than 0. And then let's look at this. See if we can figure out the limit as time goes to infinity of the function m all over 1 plus a e to the minus t. Okay? So at first, this looks a little bit complicated, but you just want to take it slowly, break it down piece by piece. You have to remember, of course, that the graph of e to the t looks like this. So this limit would have been heading to infinity. It's blowing up. But we're looking at e to the minus t, which looks like this. Okay, that's exponential decay, and from that picture you can see the limit as t goes to infinity of e to the minus t is 0. It's converging to 0. So when we analyze this part here is trying to go to 0. So if I multiply it by a constant, something twice as big that's going to 0 is still going to go to 0. So it goes to 0. So this means the denominator is just all of the denominator part is heading to 1, which is not 0. And remember, you can use limit laws and calculate limits piece by piece as long as the denominator isn't going to 0. So using the limit laws, we get the answer is m is a constant, it just stays there. 1 is a constant, it stays there. A is a constant, and e to the minus t, we just said over here, is going to 0. So anyway, we get m over 1, so that's m. All right. let's look at a few more examples for polynomials. Well, the numerators and denominators are polynomials. Those are called rational functions. This is probably the most important example that comes up. Something along this line. Calculate the limit as x goes to infinity of 3x squared plus x all over x squared plus 1. All right. The trick for this is to rewrite this and factor out the x squareds from the top and bottom. Okay? So that leaves a 3 here, and I guess a 1 over x there. It leaves a 1 there, and a 1 over x squared here. All right. Now the x squared terms, they'll cancel. Now, by the way, the reason I did this, I can't use the limit laws on the original problem because the top is trying to blow up to infinity. The bottom's trying to blow up to infinity. It's not converging to a number, so I can't use the limit laws. But when I factor out this x squared now, this term is converging to 0, and this term is converging to 0, because as x gets big, 1 over x gets really small. And so the whole top is just trying to converge to 3. The whole bottom is trying to converge to 1, which is not 0. So I can use the limit laws now, and so the answer is just 3 plus 0 all over 1 plus 0. So it's 3. Okay? All right, handy trick. There are also cases where the exponents are unequal. Let's take a look at those. So let's look at the limit as x goes to infinity of 3x squared, 3x cubed plus x all over x squared plus 1. All right. Now you see there's sort of more power on the top. They've got an x cubed appearing. The bottom only has an x squared. So let's factor out as much as we can from the top and bottom equally. So that would be an x squared from both. That'll leave a 3x plus 1 over x there. And it'll leave a 1 plus 1 over x squared here. Because I factored the same amount out, they cancel. Now the bottom is trying to go to 1 plus 0, which is not 0, so that we can do limit laws there. The top, well, this part is trying to go to 0, but this part's trying to go to infinity. So the top is trying to blow up to infinity, and the bottom is trying to divide it by something that's closer and closer to 1. So the whole thing is just going to blow up, because the top is blowing up and the bottom is just staying 1. Or even if it were 2 or 3, if you divide a large number by a constant, it's still large. All right, final example. Now, if the bottom is somehow dominant, the limit as x goes to 0 of 3x plus 1 all over x squared plus 1. Now there's more power on the bottom. There's an x squared there. The top only has an x. So let's factor out as much as we can equally. So that's just an x from each. So that'll leave a 3 plus a 1 over x on the top. And on the bottom, it'll leave an x plus a 1 over x. All right, let's analyze this. We can cancel the x's again. So the 1 over x going to 0. The 3, of course, is staying at 3. So the top is trying to go to 3. Now the bottom, this part is going to 0, so it's not mattering. Oops, this should have been an infinity. Yes. And then this x is trying to go to infinity, so infinity plus 0 is still infinity. So the bottom's trying to blow up to infinity. The top is trying to hang out at 3, so it looks like for big X, 3 divided by a huge number that's getting bigger and bigger, so 3 divided by larger and larger numbers. So 3 over infinity will converge to 0 because we keep dividing by larger and larger numbers. All right, that's it. Ciao.